about local self-attention as a replacement for graph convolution. I'm Mohammad Shamim Hussain, and I'm a PhD student at Constellia Polytechnic Institute. My co-authors are Mohammad Zaki and Shankar Subramanian of IBM. So here's an outline of what is to come. First, we start with some introductory remarks and the motivation behind our work. And then we focus on our main contribution, that is the age-augmented graph transformer framework. And then we present the experimental results, and we end with some concluding remarks and future research prospects. So first of all, our work focuses on adopting the transformer for graphs. So more broadly, it focuses on adopting the global self-attention mechanism of transformers for graphs. So why do we want to use transformers on graphs? So let's begin with what graphs are and what is it that graph neural networks do. So there are basically two aspects to any graph. There are the nodes, which might have node features, and the edges, which might have edge features. So we want to form representations of these nodes and edges. That is, we want to form node and edge embeddings. The way most chains do this is by letting the nodes communicate with each other. So now the question arises, like, how each node should look at other nodes, and how each node should aggregate other nodes. So before we answer that, let's first look at the key differences between convolution that is used in GCN and the transformer and the global self-attention mechanism that is used in the transformer. So convolution always follows a local window of aggregation no matter what's the input, whereas transformer uses a mechanism called global self-attention, which adapts to each particular input. For example, in this case, we have two sentences. In the first sentence, each refers to the word animal, so the global self-attention mechanism learns to attend to that particular word, where in the second sentence, it refers to the word street, so the global self-attention mechanism adapts to that particular input and attends to the word street instead of the word animal. So also, in case of global attention, any particular token or any particular node can look at any other token or node. So there's a long-range interaction going on between the tokens, nodes, or positions. So why might the long-range interaction between nodes be useful for graphs? One example is molecular graphs, where, for example, like proteins, where we have very long chains, and contacts may form between two amino acids that lie very far apart in the polypeptide chain. So if we are restricted to only local aggregation, we might need a large number of iterations before two nodes can see each other. Another example is social networks, where we are given an incomplete graph, and our job is to predict the missing links. But since those links are missing, some nodes may appear far apart, where actually they are not. So in this case, global self-attention can break apart from the given topology and help us look further. So let's again reiterate the differences between convolution and global self-attention. So convolution follows a pattern where each node aggregates its neighbors, whereas in case of global self-attention, each node can potentially look at any other node. Also, in case of convolution, this aggregation pattern is fixed, whereas in case of global self-attention, this pattern adapts to each particular input. In case of convolution, it's a strict pattern, whereas in case of global self-attention, it is learned from the data. But we have one hurdle to overcome, that is, in case of convolution, since we are aggregating the neighbors, we are inherently incorporating the structure of the graph in our network. Whereas in case of global self-attention, the basic transformer has no way of incorporating that. So our work focuses on adopting the transformer, or rather extending the transformer framework to include the structure of the graph directly in the framework. So now let's focus on our contribution, that is the edge-augmented graph transformer framework, which is an extension upon the transformer framework. So in the figure, you can see our architecture, that is the edge-augmented graph transformer, and it has two different types of channels. So on the left, you can see what we call the node channels, and this is usually what you see in vanilla transformers. And the reason we call them node channels is because they keep track of the node embeddings or the information about individual nodes. What we do is we extend the framework by adding something called edge channels. So first of all, we form edge embeddings for all the possible pairs, including like the existing edges and non-existing edges. So we call them edge embeddings, and we pass them through the edge channels, which keep track of this pairwise information, and this information participates in the self-attention process, and thus including the graph structure in the global self-attention process. And in return, these edge channels are also updated from the node embeddings. So the graph structure can evolve from layer to layer. This is a mathematical description of how that happens. So in vanilla GCMs, you usually have the adjacency matrix, which dictates how each node aggregates other nodes. In our case, it's replaced by the attention matrix, which is formed from the scale dot product of the queries and the keys. To include the structure of the graph, we do two things. First of all, we add a bias term to the scale dot product that is derived from the edge channels. And we also multiply a sigmoid gate, which is also derived from the edge channels. So in order to improve the specificity of our model and help it distinguish between non-isomorphic graphs, we introduced a concept known as dynamic centroid scalars. So even though the global self-attention process is adaptive, it's still just a weighted aggregation, weighted average process. And it cannot distinguish between non-isomorphic nodes such as the ones shown in the figure, because when you take the average, they form the same aggregated value. So a simple solution to this is to scale the aggregated value by a function of the centrality of the node. Since we are focusing on a dynamic framework, we don't directly use the given topology of the graph to measure the centrality. Rather, we use a different measure of centrality that's dependent on the sigmoid gates, as we shown before. And we use a logarithmic centroid scalars, that is the log of the sum of these sigmoid gates. In order to further improve the expressivity of our network, we can use positional encodings, and these serve as a global coordinate system that is an absolute coordinate system for the graph. In case of text, it's customary to use sinusoidal positional encodings, but in case of graphs, it's a little tricky to generalize. So we formulate a positional encoding scheme based on the SVD of the adjacency matrix, and this is actually related to the dot product that we find in the scaled dot product of transformers. And this framework is also very general in the sense that we can use other sorts of graph matrix, and we can also generalize for directed and weighted graphs, because the SVD of matrix is always real value. convolution um, incorporates an inductive bias where each node aggregates its neighbors. So we call it the convolutional inductive bias. And it can be useful for the smaller data sets because it imposes a strong prior on the model. But we don't want to restrict our model to this strong constraint. But for smaller data sets, it can be useful to incorporate a form of this convolution and inductive bias. So we come up with a framework where the model tries to predict the shortest distance between two nodes up to k-hop. And this actually guides the network towards a breadth-first search pattern and indirectly incorporates the convolution and inductive bias, or rather a soft form of the convolution and inductive bias. So now let's discuss the main results of our model. So this is the results on 6 medium-scale benchmarking data sets. 3 of these are synthetic data sets and 3 of them are natural data sets. And they focus on different tasks such as node classification, edge classification, graph classification, or graph regression. And there are like different parameter budgets such as 100,000 or 500,000. And all the networks are evaluated within this budget. As we can see, like our network performs best in 5 of the 6 data sets, and it performs better than the convolution models, including the recent ones such as GGN and PNN. And also it outperforms the local self-attention based models such as GT and GAT. It also outperforms a recent global self-attention based model known as Graphomer. And this is, we also evaluated our model in the large-scale framework where we experimented on the PCQ M4M and its updated version PCQ M4M V2 datasets. They are large datasets of 4 million molecular graphs, and we also compared against the convolutional models and the recent self-attention based models. So as you can see, even in this setting, our model outperforms the convolutional networks and also Graphomer. This further establishes the superiority of global self-attention over convolution. We also evaluated the transfer learning capabilities of our model. For that, we first trained on the PCQ M4M dataset, and we transfer the knowledge to other molecular datasets. Those are the OGP molecular datasets. As you can see that our model performs similarly to Graphomer, but Graphomer actually uses a specialized training method known as FLAG, whereas we simply take the trained model and fine-tune it for a very few results. And we can verify that our model performs better because of the dynamic and non-local nature of the aggregation process by directly examining the attention matrices formed. So on the left side, in the first column, you can see the adjacency matrix. In the second column, the distance matrix, and in the third column, the attention matrix. On the right side, you can see the average weight put by the network on different hops. So a convolutional neural network would only look at the 0 or 1 hops. Anything beyond 1 hop can be categorized as a non-local behavior. We see different patterns for different data sets. For some data sets, we see very non-local aggregation pattern from the very lowest layer, whereas for other data sets, we see more and more non-local behavior as we go deeper. Whereas for another data set, that is the TSP data set, we see mostly local behavior. We stress that in all cases, the network itself learns the best thing to do. That is, we don't impose the pattern beforehand. And also, even in the case where we see non-local behavior, the aggregation pattern is very sparse, similar to convolution. But at the same time, it's adaptive, that is, it adapts to each particular input. This type of dynamic and non-local behavior actually proves that global self-attention is much superior when it comes to letting the nodes aggregate each other. So we will end with some concluding remarks. So here again, we reiterate the key contributions of our work. We have proven that that the convolution inductive bias that most GNNs rely on is not an essential inductive bias, and global self-attention mechanism can serve as a flexible and more adaptive framework. We have also shown that the best aggregation pattern can be learned from the data rather than being imposed beforehand. And also, we have shown that the global aggregation method can be a global aggregation method can be superior to a local aggregation method. Also, we introduced a concept known as edge channels, which allows the structure of the graph to evolve from layer to layer, which is quite unique to our framework. Here are some future work we are focusing on. First of all, our model has the same quadratic computational and memory cost as the transformer. So we aim to reduce that using linearity or sparsity. The global self-attention mechanism that we discussed is a weighted averaging process, and we want to use other forms of aggregation such as max, mean, or standard deviation, while preserving the dynamic nature of this aggregation process. And even though our framework is very general, we only evaluated in supervised and inductive learning setting. We want to evaluate it in semi-supervised or self-supervised learning setting, such as BERT. And we also want to evaluate it for dynamic and heterogeneous graphs. So the code for work is available on GitHub, and all the datasets used are public. Thank you. If anyone has any questions.